Hello, as you mentioned, my name is Joshua Blackburn, and I work with Min Do. We're working on a project in two-dimensional geometric lifting, which has implications for image compression. One of the unique aspects of modern life is that imaging is everywhere, that we have cameras on our cell phones now, so you tend to get lots of pictures. The problem with this is that images are very large, so we have lots of data that we need to use, and so it's how can we compress this? Often, you work by compressing through a transform. You transform into some other domain, and then quantize in that domain, and then transform back. The most common one to do this is with wavelets. For example, JPEG 2000 uses the 9.7 and the 5.3 wavelet as their transform. The reason that wavelets work so well is that they tend to provide a sparse representation for piecewise smooth signals. That wherever it's piecewise smooth, you tend to get a lot of zeros, which can be quantized to zero with minimal or no loss of information. So the typical way that you can implement wavelets is by a filter bank, which I show here on the left, where you filter with H and G, then downsample, and that gets you your filter. An equivalent way for FIR filters is a lifting scheme, that you can implement any wavelet transform by lifting, which is shown on the right. In lifting, you start by separating your signal into two components, the even samples and the odd samples. And these two signals tend to be highly correlated because they're interlaced to each other. So you should be able to create a good predictor, this signal P right here. And so you're predicting the odds from the evens. Whenever you can create a good predictor, you will have a sparse representation because there will be a lot of zeros or small numbers in H. So this is an implementation for wavelets, but it's also an extension to wavelets because you can use filters for P and U that are not invertible or even nonlinear, and you'll have perfect reconstruction guarantees just by the structure you've put it in. In two dimensions, you have the issue of you need to operate on 1D filters in both dimensions. Like JPEG 2000 uses the 9.7 wavelet, which is a 1D filter. They just do it in both directions. The problem with this is the assumption of piecewise smooth breaks down at edges. When you go along an edge, the assumption is good, but across the edge, it is not. So you need to find how can we get a better predictor that accounts for edges. One way to propose on that is directional lifting. What they say is instead of going a 1D filter along the scan lines, let's do a 1D filter along some other angle. So if you took a picture of me right here, I have an edge between the short and my background, and you'd say let's put a 1D filter at this angle instead of along the scan lines. And you can get a lot of gain by doing that. This is a picture I show here on the right saying let's predict at an angle theta instead of along the scan lines. There's been a lot of work in this area as to how to pick what angle to use, and also some of the technical challenges. Like if you go at an arbitrary angle with a discrete data set, you're not going to have data everywhere you need it to be. That if you're going at 70 degrees, you're not going to get data for a long time. So you either need to restrict your angles to a specific set or use some sort of subpixel interpolation to get your data. So this works fairly well, but there are still some challenges with it. The first one is they still need to do this in two steps. They pick one angle and do it, and then they do it at a separate angle, because you need to have two sets in order to do a two-dimensional signal. But then your equivalent 2D filter is unknown, and it may have larger isotropic support. Since they're doing this as a two-step process, both of which are adaptive, it's very difficult to figure out what the equivalent 2D filter is. And even if you could, it could have larger isotropic support. Because you optimize them each independently for two different angles, your support may grow with each one of them. And also, since it's two independent optimizations at two different angles, the second one may make it more isotropic just by having two different angles. So you may have tried to design in an angle, but it doesn't stay angular because of the concatenation. On the flip side, it only exploits regularity along one dimension. Most of your signal has regularity in multiple dimensions, and one-dimensional transforms don't see that. Finally, if you use subpixel interpolation, you're assuming isotropic smoothness. So again, if I pick like a 70-degree angle and go up 1 pixel, there's not any data there. Well, I need to either do some sort of interpolation along the columns or along the rows. And in doing that, I've destroyed the fact that I was trying to go at 70 degrees, because the samples I'm picking aren't at 70 degrees. And I know that no matter what interpolation I use, it can't be at 70 degrees because there isn't data there until a long way out, which is why I had to do this interpolation in the first place. So what can we do with this? Let's start by trying to do direct two-dimensional filters instead of designing one-dimensional filters. So how would we go about doing that? First, instead of splitting into the evens and the odds, we need to split into 4 different polyphases, which I show by the square, the 2 circles, and the X in the upper diagram. And now we're going to have 3 different prediction filters. So this lifting structure on the bottom, in this case M would be 3. And we're going to predict phases 1 to 3 from phase 0. So that's predicting the circles and the X based on the information present at the squares. So that's how you can set up a 2-dimensional lifting structure. So how am I going to do this? We'll start with a very simple case. Let's say that our signal class is 2 bilinear functions separated by a straight edge. For example, this picture in the lower right. In each of the 2 parts, it's a bilinear function. In this case, you can see it's a separable bilinear function, that it could be linear in each direction. And then there's an edge at some angle, which could be completely discontinuous. And that angle of where the edge is can rotate to be any angle it needs to be. The interesting thing with this signal class is that this is equivalent to the signal class for the 5-3 wavelet and Debauchy wavelet of order 2 that have 2 vanishing moments. So this is the same type of signal class that those were designed around. So what is the innovation we're looking at? Let's create non-separable 2D filters with support aligned along this edge. So this is going to be an adaptive filter. You need to know what your angle is and designing a filter for that angle that works best in your prediction. So how do we set this up? To start with, we need to pick what angle filter we're going to design first. So looking at the picture in the upper right, I'm going to say, let's design an angle at 45 degrees. I'm going to pick 4 non-zero filter taps, and we're going to put them where the large black dots are. So every other filter tap is 0, and I'm going to try to optimize what those 4 filter taps are in order to predict well for the signal class of bilinear functions. So now I need to predict the location of one element in each of the other polyphases. So I'm going to predict the element marked by the 1, 2, and 3 in that graph to design my 3 filters based on the 4 black dots. So how can we do this? For the method following Kovacevic, we'll iteratively set each element of polyphase 0 to one of our basis functions. Because we have a bilinear class, our basis functions are 1, n1, n2, and n1, n2. So looking at this matrix equation in the middle right, the matrix in the middle, each row corresponds to one of the basis functions, and each column corresponds to one of the points. So looking for this point right here, that's the first column. If the basis function is 1, its value is 1, because all of them are. If the basis function is n1, it's -1, because you can see in the n1 axis right here, that's at a location of -1. In the n2 axis, it's at -1, so that's right there. And if we multiply those 2 numbers, we get 1. Doing that for this second point right here, for the basis function of 1, you again get 1. For the basis function of n1, it's at the origin, so it's 0. For n2, it's still at -1. And the product, n1, n2, it's 0. So you repeat that for all 4 points, and get this matrix. As long as your 4 points do not contain any 3 collinear points, this matrix is invertible. So then we go and say, well, let's predict this spot 1. We can evaluate based on those same 4 basis functions. So if the basis function is 1, the value I get is 1. If the basis function is n1, that's at spot 1/2. So I have a value of 1/2, and then you repeat that for your other basis functions. You can solve for your filter taps by just inverting this matrix and pre-multiplying that to then the vector. Then you need to solve this linear system. And the solution you get is this P1 right here. In this case, it reduces down to a one-dimensional filter along the first dimension because the point 1 is exactly between those 2 samples. Well, that happens in this case. That doesn't happen in general. You can do this same procedure for the second and third polyphase. That just means I have to change this vector. The matrix stays the same as I look at points 2 and 3, and I can get the other 2 filters shown in the bottom. And we see that particularly for filter 3, it's a non-separable 2-dimensional filter. So one of the critiques we had of one-dimensional directional lifting was you don't know what the equivalent filters are. So let's see if we do this. What are our equivalent filters? So you can use the relationships between filter banks and lifting structures to derive what the equivalent filters are. And for prediction of phase 1, we get H of 1 right here, which is a one-dimensional filter. Then for prediction 2, we get this one. And prediction polyphase 3, we get this one. A couple things to notice. First, the filters are not large. Because we don't have to deal with concatenation of directions, we know exactly these are small filters. The advantage of having small filters is when you approach an edge, you don't see it until you get really close. So it's more likely that your assumption of bilinear is actually true if you have small filters than if you have larger filters. Also, we see that the angle is at the 45 degrees we designed, except in this case we do have 2 degenerate ones that went down to 1 dimension. You can do this whole thing for a slope of something else. Say this is a slope of 2, so I go over 2 pixels and up 4. Again, they're small filters, and they're aligned along the slope of 2 that you designed in it. So they're small and not isotropic. You can also do this for another example of 1/2. You can see that it's at the angle of 1/2. So now we've designed these filters. How well do they work? Well, some things you can look at. Let's design a synthetic image that exactly fits our signal model. So it's 2 bilinear regions separated by a line at a known angle. So I decompose it with my transform and also the Debauchy order 2 wavelet. Both of these have 2 vanishing moments. So a lot of the detail coefficients are 0, anywhere except where it hits the edge. So because they're exactly 0, we can just count the number of non-zero coefficients in the detail bands, which is basically everything except the upper left corner in all of these pictures. So the leftmost column, my transform, geometric lifting, is on the top. There are 23 non-zero coefficients in the detail bands. Compares to the Debauchy 2 wavelet on the exact same signal, it had 66 non-zero coefficients in the detail bands. So this is a 3 times reduction in the number of coefficients. So I can quantize much more severely for the same distortion. You see that again for the slope of 2 and slope of 1/2, that in all cases, my transform has fewer non-zero coefficients than the Debauchy 2 wavelet. So this shows that I should be able to compress better than the Debauchy wavelet because I have fewer non-zero coefficients. Another thing we need to look at is the issue of angle mismatch. Mine's an adaptive transform, but you need to know the angle. Well, what if the angle is not quite what I thought it was? An example of this is I can't create a filter at every angle. So there's always going to be some directional error introduced. So how does that affect the result. So in this case, I designed a filter at 45 degrees, and then I put in a synthetic signal at every angle around the circle. And you can see that this is again counting non-zeros, so you want to be lower because fewer non-zeros is better. My transform is the dark line. And at 45 degrees is what I showed before. It does come out to about 24 non-zeros. We first see that this line is continuous. If there's a small angle mismatch, you're not going to have a major change in the number of non-zeros. We also see that in all cases, even when it's orthogonal to the angle I designed, it still does better than the Debussy 2 wavelet in the number of non-zeros. So in both of these were synthetic test cases. How does this work on a real image? So I took a section that seemed to have an angle at 45 degrees in order to test this. This is a section of Lena's hat, if you're familiar with the image. And so I did a nonlinear approximation where I transformed it. I kept the largest 128 out of 1,024 coefficients, and then reconstructed it and saw what the reconstruction error is. For the 5.3 wavelet, which is in JPEG 2000, it had a reconstruction PSNR of 27.4. ADL is one of the directional lifting techniques I spoke of at the beginning. It actually did slightly worse in this test case than JPEG 2000. And my transform beat both of those by almost a dB in reconstruction quality. So in this case, we see that it works well in nonlinear approximation on a real image also. We can extend this out to what is the nonlinear approximation curve for all coefficients retained. So this is a graph of the reconstruction PSNR as a function of the percentage of coefficients retained. And so we see that for everywhere between about 7 and 15%, my transform does better than all of the other transforms in reconstruction PSNR. So we see that using directionality and using non-separable 2D filters is able to give you coding gain because you have better prediction when you deal with edges. And so that should give you a better rate distortion and better compression without introducing major artifacts or distortion into your signal. So thank you. Does anyone have any questions?
Is there a question? Okay, let me ask you a question.
Okay.
So is your transform maintaining the good property of separable wavelet transform? I mean, is your transform frame or rate conditions?
That's actually something I'm working on right now. That one of the problems I'm encountering is that when you're at an angle that's not along an axis, not 45 degrees, you need to go somewhat longer. And I'm getting, it's not an orthogonal transform. And in fact, the condition number is increasing somewhat significantly. And so I have examples of cases where it's working, but it's not to the point of being a full transform that works in all cases yet. So I haven't been able to get that quite working yet. I think it will, but there probably are still some modifications that need to be made to it yet.